How are microchips made? Full CPU manufacturing process explained. Introduction to microchip manufacturing. Welcome to How are microchips made? Full CPU manufacturing process explained. In this video, we're going to take you through the step-by-step process of microchip manufacturing. A complex and fascinating journey. From the raw materials like silicon to the creation of tiny transistors inside the chip. We'll break down each stage in detail. Microchips aren't just the brains of our electronic devices. They drive performance and shape the future of modern technology. Join me as we dive into the cutting-edge processes that make these powerful microchips come to life. Let's get started. What are microchips and how do they work? Microchips, or integrated circuits, ICs, are small yet powerful components essential to nearly every modern electronic device. At their heart, microchips contain transistors, which act as tiny switches controlling the flow of electricity. These transistors form complex circuits that perform calculations, process data, and enable devices like computers and smartphones to function. The most common type is the CPU, Central Processing Unit, which acts as the brain of a device, managing tasks like processing instructions, handling input, output, and controlling other components. Other types of microchips, such as memory chips and graphics processors, serve specialized purposes but operate based on the same principles. Microchips manipulate binary data, using zeros and ones to represent electrical states. Transistors, acting like switches, control the flow of electricity at incredible speeds, allowing devices to perform complex tasks almost instantly. In everyday life, microchips power applications, enable wireless communication, and store data, making modern technology efficient and advanced. Innovations like FinFET transistors and multi-core architectures continue to push the limits of speed and performance. Shaping the future of electronics. Raw materials, silicon and its importance. Have you ever wondered what makes microchips work? The answer lies in a humble yet powerful element, silicon. This versatile material is the backbone of the modern world's most advanced electronics. From smartphones to supercomputers. But how does a simple element like silicon transform into the powerhouse inside your device? The journey begins with quartzite, a common rock composed primarily of silicon dioxide, silicon oxide. When this rock is mined and processed, it enters a fascinating transformation. Silicon is extracted through a high-temperature process in an electric arc furnace, where carbon is used to break down the silicon dioxide into pure silicon. But that's just the beginning. To create the ultra-pure silicon required for microchips, the silicon undergoes further refinement. It's melted in a high-tech process known as the Czochralski method, where it is carefully crystallized into monocrystalline silicon ingots, essentially the building blocks of every microchip. These ingots are sliced into ultra-thin silicon wafers, which serve as the foundation for all the complex transistors and circuits that make up your device. Silicon wafer manufacturing. The process begins with monocrystalline silicon, which is grown into large cylindrical ingots using the Czochralski process. A seed crystal is slowly pulled from molten silicon, allowing it to form a single, pure crystal structure, critical for high-performance microchips. Once the ingot is formed, it is sliced into thin wafers using a diamond-tipped saw. These wafers are just a few hundred micrometers thick and are carefully cut to avoid cracks or impurities. Afterward, the wafers are polished to a mirror-like finish to eliminate surface defects. The wafers are then inspected for quality, as even the smallest flaw can affect the final microchip. Once verified, they are ready for the next stages of photolithography, doping, and etching to create the complex circuits required for microchips. This delicate process of transforming an ingot into a wafer is essential for ensuring the precision needed in today's advanced electronics. The cleanroom environment. The cleanroom is essential in microchip manufacturing, where even the smallest dust particle can ruin production. This highly controlled environment ensures minimal airborne contaminants by regulating temperature, humidity, and air quality with advanced HEPA filters. These filters purify the air, eliminating potential particles that could interfere with the chip fabrication process. Workers wear full body suits, or bunny suits, to prevent contaminants from their clothing, skin, or hair. This is critical, as microchips have features thousands of times smaller than a human hair. A single speck of dust can create imperfections on the wafer, leading to costly performance failures. Every stage, from photolithography to ion implantation, is performed within the cleanroom, and tools and materials are carefully cleaned to maintain its sterile condition. The air is continuously filtered and circulated to keep the environment particle-free. Much like an operating room in a hospital. Key categories of semiconductor fabrication tools. In the complex world of microchip manufacturing, various tools and machines work together to create the intricate components found in today's devices. These tools fall into several key categories, each crucial for different stages of the semiconductor fabrication process. Photolithography tools transfer designs from photomasks onto silicon wafers with ultraviolet light, enabling the creation of precise microscale patterns. Deposition tools such as PVD and CVD apply thin layers of materials, metals, insulators, or semiconductors, onto the wafer, which form the building blocks of the chip structure. Etching tools then carve intricate patterns into the wafer using chemical or plasma etching, defining the pathways that connect the chip's components. Ion implantation tools are responsible for adding dopants to the silicon, forming the P and N regions necessary for transistors. Finally, metrology tools, including scanning electron microscopes, SEM, and optical tools, are used to inspect the wafers for defects, ensuring the final product meets high-quality standards. These categories of tools work together seamlessly to produce high-performance microchips used in modern electronics. Photolithography. Transfer design onto wafer. Photolithography responsible for transferring circuit designs onto silicon wafers. The process begins by applying a light-sensitive photoresist to the wafer's surface. A photomask with the desired circuit pattern is then placed on top, and the wafer is exposed to ultraviolet (UV) light. The UV light chemically alters the photoresist in exposed areas, while the unexposed areas remain unchanged. After exposure, the wafer is developed, and the altered photoresist is washed away, revealing the circuit pattern on the wafer. This process allows for the creation of intricate microstructures with extreme precision, enabling the production of the tiny features found in modern microchips. Photolithography, driven by UV light, is key in scaling down semiconductor components to nanometer levels, making it essential for the functionality of today's electronics. EUV, Extreme Ultraviolet Photolithography. EUV, Extreme Ultraviolet Photolithography is a groundbreaking technology that has revolutionized microchip production, enabling the creation of chips with incredibly fine details. Unlike traditional photolithography, which uses ultraviolet (UV) light, EUV uses extreme ultraviolet light with much shorter wavelengths, allowing it to print smaller, more precise features on the silicon wafer. This advancement is crucial for producing high-resolution chips that are necessary for the latest generation of electronics, including smartphones, advanced computing systems, and artificial intelligence applications. The shorter wavelength of EUV light means it can print patterns that are much finer than before, achieving smaller transistors and denser circuits. This leads to higher performance and energy efficiency, as more components can be packed onto a single chip. EUV's precision is key to continuing the trend of Moore's law, which predicts the doubling of transistor density every 2 years. Without EUV, it would be nearly impossible to produce chips with the required level of performance and efficiency for the demands of modern technology. As semiconductor manufacturers push the boundaries of chip design, EUV is becoming an indispensable tool in the quest for ever smaller and more powerful microchips. Deposition tools. Adding material to the wafer. Deposition tools are crucial for constructing the layers that form the backbone of microchips. These tools apply thin films of materials, such as metals, oxides, and semiconductors, onto silicon wafers, which are integral in building the various components of the chip, including conductors and insulators. The main techniques used for deposition are physical vapor deposition (PVD), chemical vapor deposition (CVD), and atomic layer deposition (ALD). In PVD, a material is vaporized in a vacuum and then condenses onto the wafer as a thin layer. typically used for metal coatings. CVD relies on chemical reactions to deposit materials like silicon dioxide or silicon nitride, creating highly uniform and durable layers. ALD offers extremely precise control, applying one atomic layer at a time, ensuring perfect uniformity and precision in thickness. Etching tools. Shaping the wafer. Etching is a process where unwanted material is removed from the wafer's surface to create intricate patterns that define the microchip structure. The etching process uses chemical etching and plasma etching tools to carve these patterns with extreme precision. In chemical etching, the wafer is exposed to a liquid or gas that reacts with the material on the surface, dissolving it away. This method is often used for less complex designs or where high precision is not as critical. On the other hand, plasma etching uses ionized gas, or plasma, to etch the wafer surface. Plasma etching is more precise and is typically employed for creating the intricate, high-resolution patterns required in modern microchips. Plasma etching, in particular, plays a key role in creating fine features like transistor gates, wiring paths, and other tiny structures within a microchip. The etching tools must be able to control the process with incredible accuracy, as even a slight error can ruin the entire chip. Ion implantation. Creating transistors. Ion implantation is a pivotal step in the creation of transistors within microchips. During this process, ions of specific elements, typically boron or phosphorus, are accelerated and implanted into the surface of the silicon wafer. These ions modify the electrical properties of the silicon, creating two distinct regions, the p-type, positive, and n-type, negative, regions, which are essential for transistor functionality. The implanted ions are directed into the silicon wafer at precisely controlled depths and concentrations, allowing engineers to create the precise areas where transistors will form. The p-type regions are created by implanting positively charged ions, while the n-type regions are formed by implanting negatively charged ions. These p and n regions are what allow transistors to function as switches, enabling them to control the flow of electrical signals. Ion implantation offers superior control over the doping process compared to older methods, ensuring greater precision and enabling the production of increasingly smaller and more efficient transistors. Wafer cleaning tools. Ensuring cleanliness. Wafer cleaning tools are indispensable for maintaining the integrity of microchip production. As the wafer goes through multiple stages of fabrication, particles, dust, and other impurities can easily contaminate its surface, affecting the accuracy of the subsequent processes. To counter this, specialized tools are used to remove these unwanted contaminants, ensuring a pristine surface for the delicate tasks ahead. The cleaning process often involves techniques like ultrasonic cleaning and chemical rinsing to wash away residues and contaminants, while deionized water is used for a final rinse to leave the wafer spotless. Even minute particles left behind could lead to defects that disrupt the precise patterning required for high-performance microchips. With cleanliness being a top priority in wafer fabrication, these tools ensure that the process continues seamlessly, keeping every wafer as close to perfection as possible. Metrology tools. Inspecting for defects. Scanning electron microscopes, SEM, and high-resolution optical microscopes are among the key tools used to examine the wafer's surface with extreme precision. SEM, using focused electron beams, captures detailed images of even the smallest features, enabling engineers to spot defects at a microscopic level. Optical microscopes, on the other hand, use light to magnify the wafer's surface and detect any irregularities in the intricate patterns formed during chip fabrication. These inspections are vital because even the tiniest imperfection in the wafer can lead to malfunctioning microchips. By identifying defects early, metrology tools help ensure the accuracy and reliability of the final product. In the highly precise world of microchip manufacturing, they act as the last line of defense, ensuring that only flawless chips are produced, ready to power everything from smartphones to supercomputers. Detailed step-by-step process for microchip fabrication. The process of microchip fabrication is a series of meticulous steps that combine precision and advanced technology to create functional integrated circuits. It begins with depositing silicon dioxide onto the wafer. which acts as an insulating layer, preventing unwanted electrical interactions. Next, spin-coating photoresist is applied. This light-sensitive material will later define the patterns on the wafer during photolithography. Photolithography and etching follow, where ultraviolet light exposes the photoresist through a mask, transferring the intricate circuit designs onto the wafer's surface. The exposed areas are then etched away, leaving behind the desired pattern of pathways and features. After this, deposition and chemical mechanical planarization (CMP) are crucial steps. Deposition adds additional layers of materials, such as metals or insulators, to build up the chip structure. CMP then smooths out the wafer's surface, ensuring it's flat and uniform for subsequent layers and processing. Each of these stages is critical, as they lay the foundation for the transistors, interconnections, and other components essential for a functional microchip. Skipping or improperly executing any step can lead to defective chips, making each phase vital to the overall quality and performance of the final product. Transistor physics and design. Transistor design is at the heart of microchip innovation, especially with the rise of FinFET, thin field effect transistor, technology. Unlike traditional planar transistors, which have a flat structure, FinFETs feature a three-dimensional fin-like shape that enhances their performance. This unique design allows the transistor to better control the flow of electricity, reducing leakage current and enabling faster switching speeds. The FinFET structure consists of a thin, vertical fin of silicon, which surrounds the gate, providing better control over the transistor's channel. This is crucial as chip manufacturers continue to push for smaller, more efficient devices. FinFETs are particularly important in modern microchips because they allow for scaling down the size of transistors without sacrificing performance. As microchips evolve, FinFETs have become a standard choice for the latest generations of processors, ensuring that they remain powerful, energy efficient, and capable of handling complex tasks at unprecedented speeds. This technology has revolutionized chip design, supporting advancements in fields ranging from computing to artificial intelligence, making it indispensable in shaping the future of electronics. Final testing and wafer binning. After the microchip fabrication process, final testing ensures each wafer meets specific performance criteria, including speed, power efficiency, and electrical functionality. Following this, wafer binning sorts the chips based on their testing results into categories like I9, I7, I5, and I3, based on their capabilities. The binning process helps optimize chip utilization, with high-performance chips being allocated to premium products, while lower-performing chips are used in more basic models. This classification reduces waste, maximizes chip yield, and ensures that chips meet the varying needs of consumers and different device requirements. Packaging and assembly of CPUs. After wafer testing and binning, the next crucial step in microchip manufacturing is packaging and assembly. The wafer is carefully sliced into individual chips, each of which will become the core of a device like a CPU. These tiny chips are then mounted onto a substrate or PCB, printed circuit board, where they will be connected to other components through electrical bonding. This assembly process involves placing the chip into a protective package to shield it from physical damage, moisture, and other environmental factors. The chip is then connected to external pins or pads that allow it to interact with the motherboard or device. Encapsulation materials are applied to ensure the chip is securely housed and insulated, preventing any electrical interference. The final step includes thorough testing and quality assurance to verify that the packaged CPU functions properly. The packaged chip is then ready for shipment, destined to power everything from smartphones to advanced computers. This packaging process ensures that chips can operate safely, reliably, and efficiently in a wide range of devices. Future of microchip manufacturing. The future of microchip manufacturing will be defined by smaller, faster, and more efficient chips, as the demand for advanced electronics grows. 3 nanometers and 2 nanometers fabrication processes will enable greater performance and energy efficiency. Innovations like extreme ultraviolet, EUV, lithography and quantum computing will push the boundaries of chip design. Additionally, 3D stacking and new materials like graphene may further revolutionize microchips, enhancing power and memory capabilities. These advancements will drive progress in AI, IoT, and other emerging technologies, shaping the next era of computing. Outro. That's a wrap on our deep dive into the fascinating world of microchip manufacturing. From the raw silicon to the final product, we've seen just how intricate and critical each step is in powering the technology we use every day. If you enjoyed this video, don't forget to like, comment, and subscribe for more tech insights. And as always, drop any questions or thoughts in the comments below. We'd love to hear from you. Stay tuned for more videos. And thanks for watching.